This is a tutorial on MIMO OFDM, and we will cover many aspects of MIMO OFDM. And we will start out with modeling of the multipath fading channel, and especially we'll start out with the urban environment. We will develop the HMatrix formulation and present a MIMO system. In later sections we will have a derivation of the zero forcing MIMO equalizer. We will talk about noise enhancement and MIMO performance over fading multipath channels. We will also derive the minimum mean square error MIMO equalizer and also discuss the maximum likelihood equalizer. We have an important section on singular value decomposition used in MIMO systems for beam forming. We will derive the structures for SVD, and we will also discuss the feedback of the channel state information. In addition, we'll talk about transmit diversity using beam forming. In the following sections, we will have discussions on the Alamouti Scheme for transmit diversity and also talk about cyclic delay diversity as another means for achieving transmit diversity, including receive diversity with maximum ratio combining. Throughout the discussion, we will use 802.11n as an example in order to develop a complete implementation of a MIMO OFDM system. In particular, we'll go into detail on the training for the HMatrix in order for the receiver to be able to estimate the HMatrix, and we will go into the architecture of the 802.11n receiver. And again, the 802.11n is used as a example in order to present a complete implementation of an end-to-end MIMO OFDM system. So we start out by investigating the multipath environment within an urban environment, in particular Rosslyn, Virginia. Here we show the urban environment of Rosslyn, Virginia, and these results are based on the paper on the use of ray tracing models to predict MIMO performance in urban environments that was presented in Milcom in 2006 by Carmen. And this is a great paper. In particular, it shows measurements, actual measurements that were done in Rosslyn, Virginia in an urban environment where the transmitter was located in this location here, and the receiver was moved along a 30-meter path, and the received power was measured in dBm and plotted. The carrier frequency was 1.5 gigahertz. And Rosslyn, Virginia urban area consists of many tall buildings, so there is no line of sight between the transmitter and the receivers, and the received signal at each antenna location here is received through non-line of sight through multiple fading multipaths that are combined at the receiver. Here's a look at Rosslyn, Virginia through Google Earth, so you can compare the actual image of Rosslyn, Virginia with the map in order to get an idea of the setting for the measurements that are reported in the paper. Here we show the measured received power at the receiver location based on the fixed transmitter location as we move along the path for 30 meters. So as the receiver moves along this path for 30 meters, we measure the received power, and it is plotted over here, and we see that the received power varies quite a bit over a wide dynamic range. In some cases we have deep fades, and this of course is due to the fact that we have multiple paths that combine constructively and destructively, and these paths can be either through multiple scattering or reflections or any other number of combinations. For example, we have diffraction over obstructions, and in addition to reflections we have in many cases, some cases, pass through, transmission through obstructions. If we take a closer look over 5 meters, we get the plot shown over here, and this is a very important plot because it shows that over the distance of a wavelength we go from a peak through a deep fade through another peak, and we can see that if the receive antenna moves over a wavelength, then we get a large variation signal power. So as the antenna moves over a wavelength, then we see a wide range in terms of the received power. We can go through deep fades, or we can go through some peaks. In particular, we observe that if two receive antennas are spaced apart at half the wavelength, then while one antenna could be exhibiting a deep fade, the other antenna could be receiving the signal at a higher signal-to-noise ratio. So this implies that in order to improve the communication link, we should add what we call receive diversity, that is, multiple receive antennas. Let's take a look at the next picture. In this case, we show two antenna locations at the receiver. Each one of these antenna locations receives the power from a transmitter through multiple multipath paths. For example, if they're separated at half a wavelength, it is conceivable that although the signal to noise ratio could be weak at one antenna, it could be large at the other antenna. This implies one form of diversity, which is called switch diversity, in which we have a switch which will select the antenna with the largest signal to noise ratio and then stick with that antenna. However, in this presentation, we're interested in more intelligent means of combining the energy from both antennas. That is, for each antenna, we will associate a separate receive chain, and then using digital signal processing, for example, we will combine the information in both receive chains in order to get the maximum diversity gain. An example of the case where we have multiple receive antennas and we have diversity is called maximal ratio combining, and we'll go over that in this presentation. We will also show that that is a subset of MIMO in the case where you have a 1x2 configuration and you are using zero forcing equalizer. Just as we can see that by adding multiple antennas, multiple receive chains at the receiver, we can achieve a diversity gain, it is possible to also achieve a diversity gain by adding multiple transmit antennas and sending the signal over multiple transmitters. Now, the question arises, how do we send the signal or modulate the signal between two transmit antennas in order to achieve transmit diversity? One particular scheme, which is very powerful, is called the Alamouti Scheme, in which case we use two transmit antennas and, in one particular case, one receive antenna. This is very interesting in many situations. In the case that in a base station we can afford to have multiple transmit antennas, and in the receiver, especially in cellular environments, we have only one receive antenna, yet we are able to achieve a high diversity gain, as we will show in this presentation using the Alamouti Scheme. So now consider the case where we have multiple transmit antennas and we have multiple receive antennas. So the question is, how do we combine the information at the receiver that is received from multiple transmit antennas and the fact that the receiver has signals from multiple receive chains? What is the demodulation scheme, and in particular the modulation-demodulation combination that allows us to extract the most information such that we get the highest throughput and take advantage of the fact that we have the multiple transmitters and multiple receivers? So in this tutorial we will go over the algorithms used in MIMO. In particular, we'll go over zero forcing, minimum mean square error, maximum likelihood, and also we'll talk about both open loop MIMO systems for the techniques we just mentioned, and also closed loop MIMO systems in the case where we're using beam forming, for example. So as a prelude to what we're going to get into, let's take this diagram here, which is a very important diagram. So here we're showing, for example, at the base station or access point, the fact that we're using multiple transmitters, and at the receiver we're employing multiple receive antennas with their individual receive chains. And the question is, what kind of modulation demodulation schemes can we come up with in MIMO, multiple input multiple output, that exploit the multiple receive chain and the fact that we had multiple transmitters in order to achieve the highest throughput and most reliable communication? We will show that associated with a MIMO system, a MIMO channel, we have a MIMO channel matrix, we'll call the HMatrix, which has entries that are related to the frequency response at a fixed carrier from each transmit antenna to each receive antenna. So if we look at this transmit antenna here, we see that every individual receive antenna will receive energy from that transmit antenna, each one of them going through a different multipath environment and exhibiting a different multipath fading. And here we also show the case for the second antenna, and each receiver will receive energy from the second antenna, and in fact for each receive chain it receives energy from both the first transmit antenna and also the second transmit antenna, which are shown here in color. And we can incorporate all of the multiple paths from the transmit antennas to the receive antennas into a matrix called the HMatrix. And the properties of a MIMO channel, on whether it's going to support diversity or high throughput, will depend on this channel. However, before we proceed further, let's go into more detail into the multipath fading environment. Here we're showing the impulse response for the case, like for example in the open office environment. Let's go back to let's take a look at an office environment, for example. So here we show an office environment where we have wide open spaces like in a laboratory, and then we have cases where we have multiple offices. In the case of multiple offices, we can see that if we have a transmitter located at this location here and we have a receiver at this location here, that obviously the energy that's received by this receiver can be received from multiple paths and received at this antenna location. They exhibit loss in energy as a function of distance, also as a function of loss due to diffraction, scattering, reflection, etc. And typically we see that the power delay profile of the impulse response between the transmitter and receiver has an exponential decay, and we will use this model in the developments to follow, but there are more accurate models because the environment is a little bit more complicated than that and you have actual clusters. In the case of the environment where we have multiple offices like this, we expect the RMS delay spread to be smaller than in the case of an open area like the lab here, in which case the signals have less obstruction but a longer path to the receiver, so that the actual RMS delay spread is much larger than the location over here. So depending on where you're located, your RMS delay spread would vary. For example, in this case we're showing the impulse response for the in-phase component for a case where we have 150 nanosecond delay spread. We see that the impulse response dies off. This could be the case, for example, in the open lab environment. We can also take a look at the power delay profile. In this case we're computing the actual power of the impulse response, both in phase and quadrature term, and we see that it has an exponential decay. And the modeling that we are going to use, we're going to use Rayleigh fading channel, in which case the individual delays are Gaussian distributed and exhibit Rayleigh fading. If we take a look at this power delay profile and the fact that the RMS delay spread is 150 nanoseconds, this would imply that in the frequency domain we have frequency selective fading. And let's take a look at that. So here we're showing the frequency response of the channel with 150 nanosecond delay spread over a bandwidth of 20 megahertz, and the 6.67 megahertz is just 1 over 150 nanoseconds. And we see that over the bandwidth we exhibit frequency selective fading, in which case we have multiple cases where we have deep fades and we have peaks. And down here we show the power delay profile. Now whenever we have a situation that over a wide bandwidth we have frequency selective fading, we have to come up with a modulation scheme in which we have flat fading per carrier, and that's where we use OFDM. So if we take a look at the next picture here, we're looking at the bandwidth over 20 megahertz, and what we've done is we divided the bandwidth into individual bands so that we will actually send a subcarrier through each individual band. Within each individual band we have flat fading, so the number of carriers is selected such that for each particular subcarrier we exhibit flat fading, and we avoid frequency selective fading in a particular subcarrier. And this is where we use OFDM in order to achieve flat fading per subcarrier. And this is going to be critical in the discussion on MIMO OFDM, because in general we derive MIMO assuming that we have flat fading per subcarrier. So it's very important that the carrier spacing is such that each subcarrier exhibits flat fading. So we can take a frequency selective channel over a wide bandwidth, and using OFDM we will achieve flat fading per subcarrier. Before we begin the discussion of the architecture of a 2x3 MIMO system, let's do a quick review of the single input single output OFDM system, or SISO OFDM system, as shown over here. Basically, we take the digital data, and after we assemble it into a packet, we scramble it and pass it through a convolutional encoder. For example, in 802.11a we use a half rate encoder, so the bit rate at the output of the convolutional encoder is twice the input bit rate. We pass it through a puncture block. For example, for 54 megabits per second we use 3 1/4 as a coding rate. At this point here we have 72 megabits per second, which we pass through an interleaver. We map the interleave bits into a constellation using the constellation mapper, so each point in the constellation represents coded bits. We take the carriers, we take the constellations and organize them into a 64 carriers, including the null carriers and null at DC, and we insert pilots. We take the inverse FFT, obtaining the time domain, and we add the cyclic prefix, and we have an OFDM symbol, and we transmit it over the air. And of course here we're simplifying the picture, not showing the RFIC, etc. At the receiver, we receive the signal, we remove the cyclic prefix in the time domain, we perform a forward FFT, we obtain the carriers in the frequency domain. Based on knowledge of the channel, which we obtained during training, again we're ignoring all the blocks associated with synchronization, acquisition and synchronization. We equalize the channel, and we do a demapping from the constellation points back to soft bits, which we do pass it through a D interleaver, a D puncture, and the Viterbi decoder, which corrects for errors in the channel, and we pass it through the descrambler and get the original bits. So this is the basic block diagram for a single input single output OFDM system. Now let's examine a 2x3 MIMO system. In a 2x3 MIMO system we have 2 transmit chains and 3 receive chains. If we go through the block diagram, we see, as the case before, we have a scrambler, a convolutional encoder, and a puncture block. Now the difference here is that in this case, for the 2x3 MIMO system that we were showing, we have 2 transmit antennas. The idea is that in this case we are going to double the throughput of the SISO case using a 2x3 MIMO system. Let's go back to the SISO case. So in this case we have a system in which we transmit at 54 megabits per second using a single transmitter and a single receiver. In this case we have 2 transmit paths, and what we're going to do is, to achieve high throughput, is we're going to input the signal here at 108 megabits per second. We'll scramble it, do a convolutional encoder, and puncture it. So at this point over here we have twice the bit rate as in the case of the SISO system. We'll do this as an example. The spatial parser over here would take the bit stream here and map it to 2 bit streams, one for the first transmit path and one for the second transmit path. So the bit rate here would be half the bit rate over here. So just as SISO case, we go through an interleaver, a mapper, and an inverse FFT, and we insert the guard interval or cyclic prefix and transmit it over the air. So in this case we have 2 streams at 54 megabits per second, which are transmitted through 2 antennas and are received by 3 antennas at the receive side. Associated with each antenna is a receive chain, and again we're simplifying things. For each receive chain, when we receive the signal, we remove the guard interval, we take the forward FFT, we map it into the frequency domain, and then we input each receive chain after the FFT into the MIMO equalizer. The MIMO equalizer is the subject of the current presentation, and we'll go ahead and derive the zero forcing MIMO equalizer, which will process the 3 receive chains and derive the 2 spatial streams that were originally transmitted, and then map them back to bits, combine them at the high throughput, and then go through the depuncture of a turbo decoder and descrambler. And if our input was 108 megabits per second, then our output would be 108 megabits per second, provided, of course, that the channel can support this high throughput rate. And we'll talk about that. So we're going to talk about what conditions the channel must satisfy in order to support, for example, 2 54 megabit per second spatial streams. It is very important to point out that what we have achieved here is that we are transmitting and receiving at a bandwidth of 20 megahertz, yet through exploiting the rich multipath environment between the transmitters and the receivers and using the MIMO equalizer, we're able to achieve spatial multiplexing of 2 54 megabit per second streams. Of course, that's the data rate. The actual rate over the air is 72 megabits per second. And using only a 20 megahertz bandwidth, we have achieved a total throughput of 108 megabits per second. So that is one of the key benefits of MIMO, in particular OFDM MIMO in this case. So the point here is that we're able to transmit 2 streams at 54 megabits per second and use the rich multipath fading environment to achieve spatial multiplexing of the 2 high throughput streams using multiple receive antennas and receive chains through signal processing, separate the 2 spatially multiplexed streams into individual streams and demodulate them back to a combined stream, which is twice the throughput we could have achieved in the size of case. So again, if the channel can support the multiplexing of the 2 spatial streams, and we'll go over the conditions necessary to support this situation, then instead of being limited, for example, in the case of a SISO, to a 54 megabit per second communication link, using MIMO OFDM and with a spatial multiplexing of 2 streams, we can double the throughput to 108 megabits per second. Again, provided that the channel can support that throughput. As we will show, many cases the channel can't support such a high throughput, and we will have to reduce the bit rate in each transmit stream. In some cases, we have to go to a single stream and support, for example, a diversity mode. And we will cover all that as we go along. Let's take a close look at what's going on over here. At the input to the inverse FFT, we have the carriers, which are points in the constellation, and of course we're adding the pilots and the null carriers and the null at DC. But at this point over here, what we have are the sub-carriers for each individual sub-channel of the OFDM system. If we look at this diagram, as we mentioned before, for each sub-carrier we have flat fading, even though over a 20 megahertz we have frequency selective fading. So we have flat fading for each individual sub-carrier and each sub-channel. Now from this point, as we transmit through the channel until we receive the signal at this receive antenna, for example, and remove the guard interval, we perform a forward FFT and we map the signal back into the frequency domain. So at this point over here, what we have, each sub-carrier, as it passes through the channel from transmitter 1 here to receiver 1 over here. So effectively, each carrier has been multiplied by the frequency response at that carrier frequency between transmit antenna number 1 and receive antenna number 1. For this transmit chain, at a particular carrier frequency here, the received signal at the second receive chain after the forward FFT is that carrier times the channel frequency response at that carrier. And as we mentioned, for each carrier, for each sub-carrier, we have flat fading. So let's take a look at the next picture. Consider the diagram shown over here. We basically have the MIMO transmitter in which we take a stream and split it between the two transmitters. So we have two transmitters and two streams that we are transmitting from the two transmit antennas through the rich multipath fading environment. And then we have three receive chains. In this case, we have a 2x3 system. And each individual receive chain will receive a signal from the individual transmit antennas. So for each subcarrier, it will go through the channel and it will be multiplied times a complex number, which is the channel frequency response at that subcarrier. And in this case, for the signal transmitted from transmit antenna number 1 to receive antenna number 1. So that complex number, which is the channel frequency response for that carrier frequency, is denoted by H11. That is between transmit antenna number 1 to receive antenna number 1. Let's take a look at this path here. Now, the multipath between transmit antenna number 1 and receiver number 2 is different than the path between transmit antenna number 1 and receiver number 1. And at a particular subcarrier, that subcarrier would be multiplied by a complex frequency response at that carrier frequency, in this case H21. So this is the channel frequency response at that carrier, at a particular carrier, and in this case we're considering only one carrier, between transmit antenna number 1 and receiver number 2. Similarly, we have a complex frequency response for the path between transmit antenna number 1 and receive antenna number 3. For transmit antenna number 2, again, we have a different multipath environment between transmit antenna number 2 and receive antenna number 1. However, it is very important to note, as we show over here, that receive antenna number 1 receives the transmit stream from antenna number 1 and the transmit stream from antenna number 2, which are combined at the receive antenna number 1. So let's form a matrix H, which is the channel matrix. And again, these are at a fixed carrier in which we are exhibiting flat fading. And at that carrier frequency, the frequency response from transmit antenna number 1 to receive antenna number 1 is denoted by H11. So we form this matrix here of the channel frequency responses at that carrier. We also take the two transmit streams and denote them by X1 and X2. So X1 is the carrier for transmit path number 1, and X2 is the carrier for transmit path number 2. So for example, X1 and X2 are points in the constellation or pilots. So we form the vector X comprised of the carrier for transmit path number 1 and transmit path number 2. And here we're taking the transpose, so we know that this vector is actually a 2x1 vector. Now we have three receive chains, so we will have at the output of the FFT and the input to the equalizer, we're going to have three complex received signals, which we denote by Y, so we can form a vector of the three received frequency domain complex numbers denoted by Y1, Y2, Y3. Again, these are all responses due to the carriers X1 and X2 going through the multipath fading channel with a 2x3 system, assuming that we're transmitting two streams through transmit path number 1 and transmit path number 2, and we have three receivers. Each individual receive path has independent additive white Gaussian noise associated with it, which at the particular carrier frequency we will denote as N1, N2, N3. So we form the noise vector shown here. Again, let's go back and take a look at the block diagram. So what we're seeing is that at a particular point in the constellation, at a carrier, at a subcarrier at this point, that subcarrier will be transmitted through transmit path number 1, and for example will be received by receive path number 1. Although this is in the time domain, once it goes through the FFT, it is in the frequency domain. So between this point and this point, the carrier has been weighted by the complex number H11, which is the channel frequency response between transmit antenna number 1 and receive antenna number 1 at that carrier frequency. So between this point and this point, we are all in the frequency domain, and we can simplify the picture as shown over here and then represent the whole MIMO system by this matrix equation shown here. That is, the receive vector y is equal to the channel matrix H times the transmit vector x plus the additive white Gaussian noise associated with each individual receive chain. So if we take the H matrix here and multiply that by x, so for example for y1 we obtain that y1 is equal to h11 times x1 plus h12 times x2, which makes sense. So y1 is equal to x1 times h11 plus x2 times h12. So that is equal to y1. So if you take this matrix and multiply it times the vector x, we do get the combination at the input of the antenna, but we have to also add the additive noise. So this is a key equation for our 2x3 MIMO system, which also holds for higher order MIMO systems as well.